right, folks, we're continuing with learning about the features of the graphs of rational functions. And what we're going to talk about right now in this particular video is we're going to learn about what are called vertical asymptotes. Asymptotes. Now, this is an important concept. I'm going to try and explain to you what a vertical asymptote is using a function. Let's say that we have y is equal to 1 over x minus 2. All right? First, I'm going to show you how to identify a vertical asymptote. It's really simple. Analytically, it's really easy to identify the vertical asymptote. Do you remember how to identify the x-intercepts of a function, of a rational function? Remember, the x-intercepts are where the numerator is equal to 0. So, set the numerator equal to 0, solve for x, that's where your x-intercepts are. This is very similar. Vertical asymptotes, except now it's the denominator. To identify a vertical asymptote, here's what you're going to do. Set the denominator equal to 0 and solve for x. Now here's the thing. You have to do that after you have found the holes and canceled them. Meaning, let's say that you have x plus 1, say y equals x plus 1 times x minus 2 times x plus 4 over x minus 2 times x minus 5 times x plus 7. Here, if we want the vertical asymptotes, what I've said is you have to set the denominator, this, equal to 0 and solve, right? But you can't do that yet. Look, you have a matching factor. You have x minus 2 top and bottom. First, you have to cancel the matching factors. Identify the holes. Now set the denominator equal to 0. X minus 5 times x plus 7 equals 0. And the way we solve this is set each one of these factors equal to 0 by itself. So x minus 5 equals 0, and x plus 7 equals 0. Add 5, and x is equal to 5. Subtract 7, and x is equal to negative 7. That means, here's what that means, that there is a vertical asymptote. This function has a vertical asymptote at 5 and a vertical asymptote at negative 7. So that's it. That's how you identify a vertical asymptote. You just simply set the denominator equal to 0 and solve for x. That'll give you all the vertical asymptotes. However, what does that mean? What is a vertical asymptote? Okay? Well, a vertical asymptote is a place on the graph where a place on, or let's say an x value. An x value where the function output, the values, plug in a 6, the answer is 20. Plug in a 9, the answer is 43. Okay? Where the output values move toward either infinity or negative infinity. Meaning, you start putting numbers in that are close to this number and you start getting numbers like 5 billion and 17 trillion and 943 quadrillion. Okay? The numbers are getting gigantic and they're not slowing down. They're getting larger, 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 larger. And then, when you get to the number itself, it's undefined. Okay? So, an x value where the function outputs move toward infinity or negative infinity, and where the x value point, I'm going to put in parentheses because it's not really a point, is undefined. Okay, it's undefined because it's over 0, because the denominator is 0. Okay, I think we mentioned before that 0 over a number is equal to 0, but 4 over 0, undefined, 7 over 0, undefined. Any fraction value over 0 is undefined. You cannot divide by 0. You can't divide by 0. You can't ever divide by 0. And dividing by 0 never gives you 0. Ever, ever, ever does it give you 0. It gives you an undefined point. That's what it gives you. Okay? In fact, what it gives you is a vertical asymptote. Okay? So here's what I mean. Let's look at this y equals 1 over x minus 2. All right? This. Hopefully you already wrote that down. If you didn't write it down, rewind and write it down. So, vertical asymptote. What's the vertical asymptote on this? How do we find the vertical asymptote? We set the denominator equal to 0. X minus 2 equals 0. Add 2, we get x equals 2. All right, so this function has a vertical asymptote at x equals 2. By the way, x cannot equal 2. Why? Because of a vertical asymptote. Does this look familiar? You've already had to do this. You've already done this. Okay? So now, but why? Well, here, watch this. Remember how I said that the values tend toward either positive infinity or negative infinity? Let's plug some numbers in here, shall we? What if we plug in a number really close to 2, like 1.99? So, what is 1 over 1.99 minus 2? 1 divided by 1.99. I got to put this in parentheses. When I'm plugging this in the calculator, I'm plugging in 1 divided by parenthesis 1.99 minus 2. That's what I'm doing. Okay? I'm going to use the parentheses. Minus 2 gives me negative 100 equals negative 100. Okay, let's get a number even closer to 2. How about 1 over 1.999 minus 2? That's even closer, right? All right, 1 divided by 1.999 minus 2 gives me negative 1,000. And guess what 1 over 1.9999 minus 2 would give me? Give me negative 10,000. What are these numbers getting closer? They're getting close to negative infinity. That's where they're going, to negative infinity. As you get close to that, to x equals 2, where there's a vertical asymptote, as our x values get close to 2, our values start getting either super large or super small. Negative 10,000, then negative 100,000, negative 1 million, negative 10 million, negative 100 million, negative 1 billion, etc., etc. Well, what about the numbers on the other side of 2? How about what if x was equal to 2.01? 2.01. And then what about x equals 2.001? These numbers are really close to 2, aren't they? All right, well, what's 1 over 2.01 minus 2? 1 divided by 2.01 minus 2 is equal to 100. How about 1 over 2.001 minus 2? I think you're already guessing what this is going to equal. 1 divided by 2.001 minus 2 is equal to 1,000. And if I did 2.0001 minus 2, it would be 10,000, then 100,000, then 1 million. As we get closer and closer to 2, the numbers, the output values, become larger and larger and larger. 1 million, 10 million, 100 million, 1 billion, 1 trillion, quadrillion, etc., etc. Okay? That indicates right there a vertical asymptote. Okay? Pause the video and try to identify the vertical asymptotes of this function. All right, so what do we do to find the vertical asymptotes? We set the denominator equal to 0. So x squared plus 11x plus 28 equals 0. It's a quadratic function. We can use the quadratic formula. We can factor this. There's all kinds of stuff we can do to solve this. We're going to factor it. Two numbers that multiply to 28 but add up to 11 are positive 7 and positive 4. So we're going to go x plus 7 times x plus 4 equals 0. Now we're going to set each one of these equal to 0. X plus 7 equals 0. X plus 4 equals 0. Subtract 7 from both sides, and we get x equals negative 7. Subtract 4, cancel. X equals negative 4, and that means that there is a vertical asymptote at negative 7 and at negative 4. Also note that there is an x-intercept at 0. If we set the numerator equal to 0, we get x equals 0, so the x-intercept is at 0. If we plug the 0 in here, here, and here, we would have 1 over 28. Or no, I'm sorry, we'd have 0 over 28. So that means that the y-intercept is at 0, 0, 0. Okay, all these things that we've learned. So are there any holes? No, there's no holes. We have 2x over x plus 7 times x plus 4. There are no factors to cancel in the top and the bottom, so there are no holes in this quadratic function, or not quadratic, excuse me, in this rational function. There's no holes here. So you can see how our knowledge is accumulating. We know how to identify x-intercepts. We know how to identify y-intercepts. We know how to identify holes, and now we know how to identify vertical asymptotes. The only two things you have left to learn really now are horizontal asymptotes and slant asymptotes, which we're going to get to in the next couple videos.